This is Module 33 of Mechanics of Materials, Part 1. And today's learning outcome is now, given the plane strain conditions at a point, we're going to determine the principal strains, the principal planes, and the maximum shear strain using Mohr's circle. And so here's where we left off last time. We had a condition of plane strain. We found out that the strain transformation equations came out very similar, mathematically analogous to plane stress, and so we could use Mohr's circle to depict them. So here is the Mohr's circle outline. The sign convention is the same. Tension is positive, compression is negative on my Mohr's circle, the sign convention that I'll use. For the shear strain, the Mohr's circle sign convention I'm going to use is that clockwise is positive, counterclockwise is negative. And so here's a problem. We have the measured strain components, and again, we're going to learn how those are measured very shortly in a couple of modules here. And we're going to use now Mohr's circle to find the principal strains and the maximum shear strain at this point and find the orientation of that principal plane. So here's our Mohr's circle equations. Now we have to plot, instead of plotting gamma xy, we're going to plot gamma over 2. So we're going to plot gamma xy divided by 2, which is equal to 300 mu millimeters per millimeter. And mu is just as a review, is 10 times 10 to the minus 6th. And so let's go ahead and start by plotting the vertical and horizontal face. And so for the vertical face, I've got compression, so it's minus 400, a clockwise rotation for the shear strain, so that's going to be plus 300. So I got minus 400 plus 300, and that'll be just about here. And so I'll give it V, and this is minus 400 mu, and then 300 mu. And I do the same thing for the horizontal face. Now I have positive 1,000 and counterclockwise, so negative 300. So I go out 1,000 and down 300, and about there. So this is the horizontal face, and that's going to be 1,000 mu and 300, minus 300 mu. I can now draw a line between those 2 points, and I can draw my Mohr's circle. And see how well I can do at a circle here. Not so good, but you get the idea. Okay, I can find the center now. That's epsilon x. Epsilon x is minus 400 plus epsilon y, which is plus 1,000, divided by 2, and those are times mu. I may forget on occasion to write the mu, but it's always times 10 to the minus 6th, and 0. So that's going to be equal to 600 divided by 2 is 300 mu and 0. So here is our center at, and let's do this in blue, center at 300 mu and 0. We can now find the radius as well. So I've got the square root of epsilon x is minus 400 minus 1,000 divided by 2, and that's all squared, plus gamma xy over 2 is 300 squared. And if you do that math, you'll find that the radius is equal to 716 mu. So now if I come up from my center with the radius of 716 mu, this is the max of gamma over 2, which is 716 mu. And so that means that gamma max, and let's again write this in black, gamma max is 2 times that, or 1,432 mu radians, radians being dimensionless. And so that's one of our answers. NS. Okay, so that takes care of the max in-plane shear strain. Okay, we've got to be careful and make sure that we say in-plane shear strain. Now, the principal strains are going to be here and here. So I'm going to add the radius to 300. So that's 300 plus 716, or 1016 for epsilon 1. So epsilon 1 is equal to 300 mu plus 716 mu, or 1016 mu. Again, I'll say millimeters per millimeters, but that's actually dimensionless, and it's tension since it's positive. So that takes care of one of our principal strains. And the other one is back here. And so that's going to be 300 minus 716, or epsilon 2 is equal to 300 minus 716, and again, mu, or minus 416 mu, which is 416 mu millimeters per millimeter. And since it's negative, it's going to be in compression. That's the second principal strain. And the last thing we want to do is to draw this on a properly oriented stress block from the plane that we know. And so we've got, here is going to be our rotation on Mohr's circle, 2 theta sub p. So in finding this 2 theta sub p, we use the trig function sine. Our opposite side here is going to be a value of 300. The hypotenuse is 716. So we've got sine of 2 theta sub p equals 300 over 716. So if you do that, 2 theta sub p ends up being 24.8 degrees on Mohr's circle. That means it's going to be half of that, or 12.4 degrees on the stress block. And we're moving from the horizontal face in a counterclockwise direction. And so now if I draw my properly oriented stress block, this angle is going to be 12.4 degrees. And when we move 12.4 degrees on this horizontal face, we're going to have a tensile strain 1016 mu, and no shear stress, no shear strain there. If we go another 90 degrees on the stress block, or 180 degrees on Mohr's circle, we've got negative 416, or 416 inwards mu for our other principal strain. And so you'd have the same on the opposite sides. This would be 416 mu, and this would be 1016 mu. And so that's our example. In fact, let's just label this as the horizontal face, and we move from there. And so that's a good example of finding the principal strains and max in-plane shear strain. And we'll come back and do part B next module.